Hey guys, welcome to Great Learning. SciPy is a fantastic library in Python. It's short for scientific Python, and as the name itself suggests, right? When you think about Python, when people call it the world's most powerful language, the world's most popular language and all of that, you have to understand that all of these power comes from libraries such as SciPy and of course the hundreds of other libraries that are there. Now, these libraries, what they basically do is whenever you're working on solving a problem or whenever you're working on, creating an application or something like that, it simplifies your process. I definitely want to say that it simplifies your process by 10 folds because you'll be probably writing 10 times as less as the code that you would have written without the library. And of course, it's not just that it's less code, it's the fact that it's an efficient way to go about tackling, an inefficient process, let's just say, right? Maybe creating an application is huge, but the way you can break it down into simple stuff using libraries and to work on it is fantastic. SciPy is a very popular library which has a wide variety of application. When you think about statistics, it's extremely popular. When you think about signal processing, when you think about image handling, right? Who would have thought? So it is a library which packs a punch. You can work with statistics, you can work with linear algebra, you can work with images, you can work with a lot of different things. You can work with signals. Signal processing is a very, very important part of the analog and digital electronics world we have today. So you can already see that, just from the introduction, just from the last 2 minutes of my talking, you can already understand that this is a library which definitely has an impact in almost all the other domains that we have out there, right? Because wherever in either of the domains you take a look at it, you would require statistics, you would require some form of signal processing or handling, you would require some sort of image editing, you would require some sort of solving mathematical equations, linear algebra, integrations and all of that, right? So either if it's not all of this, it's a one part of it, and eventually SciPy can handle all of that. So it's a very important library for all of you all to learn, and hence we here at Great Learning understand the importance of this library, and we've come up with this course SciPy in Python to make sure that you guys are very clear with all the foundationals, and of course you can get along understanding all the theoretical bits and all the practical bits that we're going to be discussing on this course as well, right? If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleagues, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments. So guys, I hope you guys are excited for this course. My name is Anirudh Rao. Without further ado, let's just take a look at the agenda for this course, right? Well, coming to the agenda, SciPy in Python, we're going to start this course out by actually understanding what SciPy is. Now, ladies and gentlemen, whenever you try to attack a new library, whenever you try to understand a new library, it becomes very important that you take it really slow, you understand it completely, because once you're clear with these foundations, once you're clear with what the library can do, and I'll be showcasing you guys a lot of things about how things work here in SciPy as well. Once you have these foundations cleared out, right, that's when you can start using these libraries for any application or anything that you want to build. So to begin this, we're going to start this out by understanding what SciPy is. And after understanding what SciPy is, we're going to be diving headfirst into understanding, first of all, how we can go about installing SciPy. It's a very simple process. I'm sure that all of you all can follow along very easily, right? So once you have SciPy installed, there are, various sub packages that SciPy brings to the table, and it is these sub packages that give the library its entire power. For example, there are various ways of how you can create handle clusters, working with constants, taking a look at something called as FFTPack. We're going to be taking a look at the concepts of interpolation, and the thing that you see there which says Linalg, that basically stands for linear algebra. So we're going to be taking a look at that as well. And Ndimage talks about how you can get to do basic image processing with SciPy as well, right? So all of these sub packages, all of these tiny things that you can do in SciPy SciPy, when you look at the big picture, that is when once you bring these together, right, that's what makes SciPy really powerful, right? So guys, I hope the agenda is very clear. Without further ado, let's get started with the first item on the agenda, which is what is SciPy. So coming to understanding SciPy as a library itself, right, one thing that I should tell you at this moment right now is the fact that SciPy is an extremely popular library in Python. There's thousands and thousands of users, and when you say it's a library that is really popular, definitely you have to give reasons of why it is popular, right? Now, the entire scientific community, they required a library through which you can perform certain tasks which you had to do manually otherwise, right? Think about working with algorithms, think about already having functions which definitely will do the task for you, right? So sometimes, what is a function, right? When you think about a function, it's basically having an equation, solving a lot of things, and eventually getting a result after you provide a certain input. That entire process from input to output will be automated if you have readily built functions that can take up the task, right? So that is possible here as well. And when you think about working with the interactive Python sessions that are out there, right? So what SciPy does, the biggest advantage is that it provides us with high-level commands and classes which we can use to not only just visualize data, but also manipulate it and work with it in real time. Now I'm going to be showing you all the demonstrations, practical demonstrations through which you can see for yourself that, hey, yes, SciPy is a library which is very powerful, and it definitely sees its fit in multiple domains out there, right? So whenever the world talks about scientific computing, whenever the world talks about technical computing where there is a requirement of Python, you can be rest assured that SciPy will be the library that's going to be popular there. Now, after you've understood this about SciPy, here's a very interesting fact you may or may not know about the library. SciPy is basically built, on top of NumPy, and therefore, whenever you have a situation where you have to use SciPy and NumPy as well, right? If you just import SciPy, you're good enough. You can work with all the functionality that NumPy brings to the table, right? In the data visualization scene, if you know that Seaborn is built on top of Matplotlib, right? Similarly, here SciPy is built on top of NumPy, so it brings all the functionality of NumPy and then some, and that definitely is making it's adding more efficiency into the pipeline, and at the end of the day, it's simplifying not just the way you work with Python code, but the syntax through which you write, right? That is becoming more simple as well. So guys, with that introduction to SciPy, let us quickly come to a section where we can discuss how you can go about installing SciPy. Now, there are many ways about installing SciPy, and the biggest advantage is that just like Python, SciPy is supported across multiple operating systems that we have today. And of course, you can have a list of operating systems, but I'm going to be picking up the top 3 operating systems that we have today. One is Microsoft Windows. We have all the Linux flavors and distributions, and then we have Apple's Macintosh, right? Mac operating system. So, if you're using either one of these, I'm sure, you guys viewing this, you'll be using all 3 of these, or you have definitely used either 3 of these, right? So it's going to be a real simple process to install it. We're going to be dividing the installation into 2 steps. One place, where we'll be discussing for Windows and Linux, and the other one is slightly separate because Mac and Apple has their own architecture to play with, right? So coming to Windows and Linux. Now, one very good thing about Windows and Linux, and of course, whenever you're working with the Python command line here, is that you have this ability, you have something called pip. Pip basically stands for package installer, right? Pip, in fact, it's a recursive acronym which stands for pip installs packages, PIP. Pip installs packages. So it is basically a package installer, a package manager, which will help us install all of these libraries at ease, right? The advantage that pip brings to the table is that it's a standard package manager, as in it can be installed very easily on Windows, on Linux, and more, right? So to basically, to install SciPy using pip, all you have to do is run one simple command that you can see on your screen right now. Look at the last line, which is in bold. It says pip installs SciPy. It's literally these 3 words, and with these you can definitely clear up. And I'm sure if you've if you're watching this course, you might have had some experience with pip and installing packages. So again, it's a very simple and a very straightforward process of how you can install it on Windows and Linux. But there isn't, there's more advantages to Windows and Linux. The fact that we have Anaconda distribution, right? Anaconda is an absolutely fantastic distribution, which will not just give you everything you require in Python, but it will also give you other libraries, other helpers, other tools, other frameworks, and it brings a lot to the picture through which you can start, creating applications. And eventually with Anaconda, right? When you start working with Anaconda's distribution, it's a fact where it'll already come built with multiple libraries that you don't have to work with. Now, installing SciPy in Anaconda is very, very simple. All you have to do is go to Anaconda's website. You have to download something called as the Anaconda Navigator. And once you open it, start installing, you will have something called as the Anaconda prompt. Anaconda prompt is very similar to the command prompt or the Python CUI that you would have seen. Again, once you do all these steps, it's a very simple step of running one single command, conda install Anaconda SciPy. And that is it. As soon as you run this conda command or either the pip command, regardless of both ways, you will have SciPy installed and set up on your Windows. And it is the exact same steps that you'll be following for Linux as well. Now, if you're wondering, yes, Anaconda is available for both. It's available for all these Mac users. It's available for Linux. It's available for Windows and a lot of other operating systems as well. So again, you have one more way of doing something which is already simple, right? That, it's fun when you think about how simplified the process of setting everything up is these days, right? So, Windows and Linux aside, let's talk about Mac OS for a second. I'm sure, you viewers are, probably, watching this on your Mac right now. So, the slight disadvantage with Mac is that it doesn't come pre-installed with any package manager out there. So, what you can do to sort of work around the small disadvantage is that you can install your own package managers there, right? So you can see two commands. You can see a couple of commands on your screen right now. If you actually head to the terminal and run these commands, guess what? With just these one command, right? The sudo port install command, you can go about, installing 3 libraries, 4 libraries, SciPy, Matplotlib, Pandas, and the NumPy library as well, right? Again, it's not a step where you have to break your head. You have to do like 100 different things to install the library. You just have to open up the terminal. You just have to copy paste what you see and eventually hit paste. And you're done, right? How simple is that? And doing that will set everything up in SciPy that you will require, to follow along with all the demonstrations that we'll go about doing it, right? And one advantage with Mac, I wouldn't say advantage, it's a slight helper is for a fact that just like Windows and Linux, where we had multiple ways of installing, here also you have multiple ways of installing. You can use Homebrew to install all these packages, right? But one thing, again, a small disadvantage here by using Homebrew is that whenever you try to install SciPy through Homebrew, it'll not bring the entire library, right? Now, SciPy is a huge library, as you're going to see through the rest of the course. Of course, we're not going to be covering every single thing in detail, but we are going to be covering all the really important stuff that you guys have to know. And to get to that point, if you're using Mac, again, we have one command, brew install NumPy, SciPy, IPython, Jupyter, right? Now, this will install a lot of things. It's going to install NumPy, which is the library. It's going to install SciPy, again, which is the library under discussion. IPython stands for interactive Python, and we have Jupyter, basically a Jupyter notebook server client architecture there, right? So all of this is installed to you again using one command, and you really don't have to put a lot of effort in setting it up. Right? Now that we have some clarity on knowing what SciPy is, knowing where it is used, what it can do, and a bit of how we can go about installing it as well, and hoping that all of you all have SciPy installed at this moment, we can jump right into the next section where we'll be discussing all of these sub packages in SciPy, which is literally at the heart of the concept, right? Without knowing these, there is no understanding SciPy at all. So talking about the sub-packages in SciPy, one advantage is that SciPy supports multiple sub-packages that are out there. Now, there are many dedicated software tools which become necessary whenever you're working with scientific computing, right? Just the term scientific computing seems very complex to think about it, but when you have to implement it in Python, of course, you cannot just have one library. You cannot just have one single entity, tool, or technique that will always work for all the solutions. It doesn't happen, right? So what SciPy does is it is considered as a very important tool. It is considered as a library, which is not only just providing one single aspect of it. It's not saying, hey, just use statistics, just use image processing, just use this, right? It's offering multiple Python modules that you can use, and you can use all of these at once if you choose to tackle everything that's required to perform scientific computing or any sort of technical analysis that's required as well. This is a very popular tool to be used, right? Now, look at your screen. You have multiple sub-packages out there. Of course, we're going to be discussing a couple of these in a small bit of detail, but you have to understand that each of these are used in their own specific purposes, right? Now, you have clustering algorithms. Clustering is a very important part of machine learning, right? You've used clustering again. Just think of a simple example where you're given a couple of fruits and people say, hey, can you put all the oranges on the left side? Can you put all the apples on the right side? Can you keep all the bananas at a different place? You can do that, right? If you can do that, you basically know what clustering can be. There's various types of clustering. There's hierarchical clustering, divisive clustering, agglomerative clustering. There's a lot of types of clustering, but what you should know is that SciPy is going to be giving you a lot of functions and a lot of easier ways to go about doing everything that I said, right? And since we're talking about scientific computing, of course, there's going to be a good amount of physics involved as well. So wherever people are using Python for physics solutions, guess what? SciPy is also providing certain mathematical constants that you can use, right? Now, we all know the most famous constant out there, pi, right? Pi is 3.1418. So on and so on. Now there's there's a lot of constants if you think about it. There's Boltzmann constant. There's a lot of numbers out there. All of these complex stuff. There's Chandrasekhar limit. There's many concepts. And if you are a astrophysics geek like me, you will definitely be familiar with how complex things can get there, right? So SciPy is providing a way of handling all of that easily. And FFTPack, if you're wondering what FFT stands for, basically it stands for Fourier transforms, right? Fourier transforms are a very, very important part of, handling and working with differential equations. And if you've ever used that, or if you're trying to solve differential equations using Fourier transforms and you want to, apply all of these transforms, Fourier transform, inverse Fourier transforms and all of that, you have helpers out here that will help you do it easily, right? And Fourier transform is a part of mathematics, but another very important part of mathematics that you might have studied in school or college is integration, right? So for all your integration requirement, there is again another sub-package called SciPy.integrate. And if that wasn't enough, guess what? Look at it, right? We have more. We have one thing to perform interpolation. We have another library, Linalg. Again, as I just told you, right? Linalg stands for linear algebra. So for all your linear algebra routines, you have a sub-package ready to go. If you have a requirement where you have to work with a lot of data input and a constant source of data filtering and data outputs, you have SciPy.io as well, right? IO talks all about how you can handle data inputs and outputs. And then you have Ndimage. Ndimage basically stands for n-dimensional image, right? So it's, you can work with images in 1 dimension, you can work with images in 2 dimensions, 3 dimensions, and all of that. So whenever you are working with multiple images, I'm going to be showing you all of these practically, but for now, to quickly give you a picture about what it is that you can expect going ahead, right? We're going to be discussing a couple of these libraries. Let's pick up 5 or 6 of these which are super important for you to know in SciPy, and eventually we can get started with that, right? And if that wasn't enough, there is more. There are more sub packages, right? There's ODR, which basically stands for orthogonal distance regression. You have direct optimization helpers, and look at SciPy.signal, right? I told you it plays a very important role in signal processing. We have a sub package that does just that. We have sparse. Whenever if you have worked in detail with applied mathematics, there's a very good chance you might know what a sparse matrix is, right? So handling all of the operations that it brings can be done easily as well. And whenever you're working with data structures and algorithms, we have a library for that. Any sort of other special functions that you can think, we have libraries for that as well. And stats, of course, talks about statistics. Weaves talk about how well you can perform certain writing tasks. by making use of these sub packages as well, right? So let me just quickly go back here, and you can see that each of these sub package can work as a standalone sub package, work in dependency with all the others. So depending on, you might be asking right now saying, so how will I know what sub package I should pick up for my applications? Well, what it is that you're doing in your application will directly influence what sub package you might be using. If you're working with signal processing, it is clear as day that you're going to be using this. If you're working with statistics, you have a package for that. If you're working with image processing and you want to use a bit of SciPy there, again, you know which sub package to go about now, right? So I hope this quick introduction to tell you that these are the sub packages which give power to the library are clear to all of you all. So without further ado, I think it's high time we jump right into understanding each of these, not only just theoretically, but practically at the same time, right? So let's talk about SciPy cluster. Now, ladies and gentlemen, clustering becomes a very, very important part of SciPy, of Python, of all the practical applications we have in today's world. Clustering talks about how you can take one common data set or a heap of data and how you can divide it based on certain data points, based on similarities, based on dissimilarities to other groups as well, right? Now, think about the apple, the orange, and the banana example that I gave you. An apple as a fruit is fundamentally different to an orange. An orange is fundamentally different to a banana, right? So when you bring it all together, it's a jumbled pack. But when I say, hey, I want clusters of different fruits, that's when you know you get to pick all the similar characteristics, right? Now, when I say, hey, keep all the bananas aside, it can be raw bananas, it can be ripe bananas, everything. Now, I'm asking you to filter it and cluster it based on the type of fruit, not based on the type if the fruit is either raw or if it's ripe or anything like that. And if that were the case, guess what? You can have more clusters to go about doing this, right? So whenever you do these, whenever you take this entire basket of fruits or anything for that matter, put it out into separate entities, each of these separate entities that we have in discussion right now, as you already know, they are called as clusters, right? So working with clusters, handling clusters becomes very, very simple in SciPy. And at this moment, you might be asking a question saying, okay, so clusters is a very wide term of how you can go about using SciPy. Is there any further modularity that will help you understand? Well, yes, there are two types of clusters that are out there. We have central clusters and we have hierarchical clustering as well, right? Now, let me give you a small example to tell you what we're going to be doing. Now, we'll be talking about a demo where we'll be using NumPy to generate set of random points. What we are going to be using is, after creating two sets of random points, we're going to be joining all of these and eventually we whiten the data. What basically whitening the data means is that whenever you take a look at a lot of data points, right, it usually has a way of distributing itself. Think about normal distribution, think about other distributions, right? So each of these distributions bring its own characteristic, and that characteristic is what gives Python, is what gives library the understanding, the fundamental understanding about what is going on with the data, right? Now, you look at data, you understand it. I look at data, I understand, because we have trained as humans. Your machine isn't, right? So to get to a point where it can figure out certain patterns, we require whitening the data. Now, whitening, as I just told you, it takes like a lot of data, it groups it, crunches it into a certain workable range, and this workable range becomes very critical for us, be it in binary operations, be it in non-binary multiple categorical variable based solutions as well. Now, k-means clustering is a very popular way of how you can go about clustering. And what we'll do is we're going to take all the data that we just took together and we eventually brought it together. We whiten the data. Now what we'll do is we're going to be using the k-means functions and just pass all of the data to it and eventually give it the number of clusters that we want. And those many clusters will be created at the end of the day. So what are we doing? We generated a couple of random data. We eventually brought it together. We ran it through k-means clustering. And after that, we ran it through a function where we can go about talking about how divisive and to what level of modularity that you require with the SciPy clusters that we're talking about, right? So guys, it's not just theory. Everything that we're going to be discussing from now on is going to be practical as well. So let me quickly open up Google Colab. Google Colab is nothing but a Jupyter notebook that is hosted on the Google Cloud platform, right? So it's basically your regular Jupyter notebook, but it has many advantages, and it works on the Google Cloud platform. So you don't require extremely powerful CPUs, GPUs or anything to work with efficiently as well. To a certain extent, to 95 or 90% of the users, to all the applications that they are going to be devising using Google Colab, it is free. But of course, there's pro plans and all of that. But for now, for everything that we're going to discuss, the free version of Colab, and it's majorly free, right? Only a small chunk of people who require high amount of processing RAM and storage, they prefer the paid version of Colab, but for the rest of us, this should be fine. So let me quickly open up Google Colab and we can discuss this exact example that we have in consideration. Alright guys, so as you can see, I just quickly opened up Colab. Colab, you can just follow through the same URL, colab.research.google.com, or just go to Google and type Google Colab, COLAB, and it will bring you here, right? So as you can see, we're going to be discussing a lot of, a lot of these sub packages practically as well. But to quickly talk about clusters that we have, right? Now we discussed what we're going to be doing already. And whenever you're working with any sort of solution, the first step that you have to do is import all the libraries that you're going to require, right? Importing SciPy, importing NumPy, Matplotlib, Seaborn, and all of these libraries which we require to work with. As I told you, we're going to be creating two clusters, A and B, filled with 50 random data points, right? 50 each. Overall, we'll have 100 points. 100 is being divided into two, and each of these is getting into one cluster A, and each of these is getting to one cluster B. And after that, we're going to be normalizing the data. Once we go about normalizing the data, now we have to understand, okay, so how can we go about creating clusters, right? So you have two very different data points which are random, but there has to be certain patterns and there has to be certain ways you can go about performing clustering using k-means, which will eventually create the clusters that we require, right? Now we're going to be using these two clusters to find data, find similarity, create clusters, and all we're doing is we're creating a plot to showcase to you guys how we can go about doing, right? Look at the logic, right? The logic basically is 1, 2, 3, 4, 5 lines. When you think about the entire thing, less than 10 lines is the heart of your logic, where you can create random data, create clusters, run it through k-means, eventually even provide a data visualization. Now, my goal here is not to walk you through each and every single line of code of what it means, because I'm sure if you are here at this moment of time, if you're looking forward to learning Python, you might know a bit about reading Python syntax and understanding Python's syntax, right? Now look at this. We had two very different data points, and here you can see that it has created two clusters for us, right? This is a graph that is showcasing what each of these points were mapped, and once the points got mapped, where were these clusters? So you can see these two red dots, which is basically plotting the center of these two clusters at hand. And again, 5-6 lines, and we can do a lot of these things, right? Now imagine you had to get to this result, but you had to do all of it manually. That would have been a pain, right? Because at the end of the day, you have to write a lot of code to not get a lot of output. But here it's the reverse. We are writing a small amount of code to have a very large output, right? So guys, this is SciPy Clusters, a very simple demo to showcase to you guys about how you can go about working with that. Now, the next thing that we're going to be doing after understanding SciPy Clusters is we're going to be taking a look at SciPy Constant. As I told you, whenever there's a requirement of you working with multiple constants, mathematical constants, constants in physics and all of that, at the end of the day, everything is a mathematical constant. But, these values which have a certain significance and they don't change, there, as I told you, there's hundreds of constants, and it becomes inhuman. It becomes impossible for someone to memorize what each of these constants are, right? They're very complex decimal numbers when you look at it, 3.1418, or it just keeps going and going in many cases, right? So what is the way of how you can simplify this? One way of simplifying is you don't have to remember what the constant is. If you know what constant you require to be used in your application, in your solution, which of course you will know, it's as easy as importing it, finding its value, grabbing the value, using it for your applications. How simple is this? Right? So it's not just one or two constants that's actually provided in Python. There's various types of constants. SciPy.constants subpackage itself is a very, very popular subpackage. And whenever anyone is talking about the use in the case of general scientific purposes, this library this subpackage is very popular there, right? So let's quickly take a look at how we can work with these constant variables, how we can import it, and how we can go about using it. But just before that, I want to also tell you that these are some of the constants that you can work with and you can take a look at as well. We know C, E is equal to mc square, Einstein's relativity. The C talks about the speed of light. You can have various physical constants that talk about it. G is basically the Newton constant for gravity. E talks about elementary charge, molar gas constants, Avogadro constant, Boltzmann constant, electron mass, neutron mass, Planck's constant. Look at this, right? It is absolutely a treat. If you're a person who's into physics, if you're a person who wants to use the world of computing, the world of IT to simplify something in an already complex world of physics, you have all of these constants right at the grab of your hands to go about working with them in an easy fashion, right? So let me quickly open up these cells here and we can go about working with it. Now, one constant that you would have seen in the world is something called as the golden ratio, right? The golden ratio is basically like a spiral which talks about having, it talks about almost everything in the universe having a certain pattern that you can trace and come about, right? It's called as the golden ratio. Now, the golden ratio is a very simple number actually. At the end of the day, it's 1.6 something. Yes. So it's 1.6180. And this is a number which again talks about, many cases where you're trying to, this number is very important. If you're trying to design a room for a home theater, for say, it has to be some specific dimensions. Whenever you go to a theater, it's not just randomly built. There's a very good chance someone, if it is designed properly to the utmost care, they would have used something called as the golden ratio there as well, right? So now I am a huge fan of theaters and all of that. So I just thought this is a good example to show you guys. Now for all you physics buffs out there who are saying, hey, show me a physics example, well, guess what? The Boltzmann constant that we just discussed, right? Look at this. It's just one line. And this command find is basically telling us what all it has, anything which has the name Boltzmann in it. And as you can see, right, you have Boltzmann constant and you have it in multiple SI units out here. SI unit is something that you would remember, right? Whenever we talk about temperature, it's degrees Celsius. Whenever you say EV, I think it's electron volts, and K stands for Kelvin. Hertz is a measure of frequency and all of that, right? So what it is basically saying is, hey, when I say, hey, tell me all the Boltzmann constant types that are out there. So the constant is going to be the same, but the value of the constant is going to change with respect to various SI units that you're going to be using, right? Various situations that it's going to be used. So it is telling me these are all the list of constants that you can use in terms of Boltzmann. I say, hey, okay, so now I know what constant I require it. I want it in Hertz per Kelvin. And as soon as I hit, play here, it's giving me the constant value that's out there right now. How simple do you think this is, right? At the end of the day, you don't have to break your head about remembering, a very complex number such as this. And that itself is a small advantage. And as you can see, with another advantage is Google Colab is all you have to do is move your mouse to the code and it will basically tell you how many physical constants that are out there. It'll tell you it's 444 physical constants that it has, right? Just like Boltzmann, you can pick up all the constants that I just showed you, speed of light and all of that, and you can have some fun with it. Right now, I want you guys to get your hands slightly dirty, and since it's just 2-3 lines of code, right? Overall, the entire thing is 3 lines of code. 1, 2, 3. That's it, right? Now, I want you guys to go about doing this for other constants that we just discussed. So quickly rewind back to the part of the video where I showed you the other constants. Try to figure out for yourself how you can go about doing it. It's very simple. You have to change 1 or 2 tiny things, and I am confident that all of you all watching this will get about how you can go about doing that, right? Fantastic. Next, let's quickly talk about Fourier transforms, right? Fourier transforms basically FFTPack, as we already told you. FFT. If you're wondering why we have 2 F's, the first F stands for fast Fourier transformation. So whenever you're working with these algorithms, whenever you're working with generic computing and specific scientific applications, you're gonna be using multiple mathematical techniques to go about doing it. DFT is a mathematical technique where you take all these spatial data around you and you take the spatial data, convert it into frequency data. Now, I'm not going to be going into the depth of telling you, why they'd be doing this or how it is done in a detailed way, but a very simple example to show you how you can go about calculating the Fourier transformation is very simple. Now, let me quickly take you back to your school days or your college days where you might have read about these trigonomic functions, right? You have sine, cos, tan and all of that, right? So here what we'll be doing is we'll take a periodic function of sine. You know what a sine wave looks like, right? It's the AC power that you're getting at your home. It's a sine wave at the end of the day. So we're going to be using a simple periodic function and we'll see how we can use Fourier transform to transform that sine wave that we're going to be seeing into something else. Now, do not worry if you do not pick up on the nitty-gritty details out here. This is a very niche application of it, but at the end of the day, this is very important to know for you guys as learners, right? Now, let me quickly open up FFTPack here, and in FFTPack, we have one or two demos, right? Let me zoom out a little so we can see the entire demo at one point of time. As you can see, starting, it's all just us importing libraries, and then as I told you, right, we're gonna be converting spatial data into frequency data, so you're gonna have to have some frequency. And what is the unit for frequency? Hertz, right? The power in your house, the sine wave power that you get in your house is either 50 hertz or 60 hertz depending on where you live, right? And then the sampling rate. Sampling is again a fantastic part of working with these analog and digital electronics if you have studied about it in college. And all we're trying to do is we're trying to take spatial data, convert it into simple frequency data, right? And look at this. This is what it might look like. Now, if you do not know what amplitude and all of that means, do not worry. Just look at the graph and understand that this is sort of something similar to what it would look like if you could see the power coming in through the wires to your house, right? It's a simple sine wave that all you're trying to do is, and we've just plotted the amplitude, we've just plotted the time out there, and it's simple, right? Now, the important part here is this is great. We have the sine wave, everything is good. Now, what we need to do, you have to understand is that we have to take this data. This is spatial data. We're talking about how the wave varies with respect to time and with respect to how much it moves and the power it gets. That's amplitude, right? So what we do here is we basically say, okay, so this is what you have as an input, a processed input. Now, what's going to happen if you do have to convert it into frequency data, right? Look at this. As soon as you say, hey, here is the magnitude in terms of all the spectrum that this is generating, and here is the frequency in hertz. Again, we just took this, we use FFTPack, and all you have to do is Fourier transform, just converted spatial data to frequency data, and it did it in what? The logic is basically 2 lines out here, and the logic here is basically again another 1 or 2 lines, right? See, 4 lines at the end of the day. Now you might say, hey, it's not 4 lines, we have 20 lines totally. But all the 20 lines out there, these are like boilerplate code, which again, once you start learning it and once you start doing it, your brain will not have to put any effort to understanding how that's gone about doing, right? So it's very simple. You take spatial data, you convert it into frequency. And if you're wondering about, why would someone do this? How is this done? What application in physics? You'll have to do a bit of reading on that yourself, right? Now, I'm a data science guy and I'm definitely not a physics guy, but I love astrophysics if you want to know. All right, cool. Now that we're done with FFTPack, let's quickly take a look at the next thing wherein we are going to be discussing a little bit about interpolation. Now, interpolation is one of these concepts which is again super popular because when you have 2 values, right? Whenever you have 2 known values, let's just say 0 and let's just say 10. When you have 2 values, there are a lot of other values, right? There's infinite values between 0 and 10. But what if you had to estimate unknown values that are present in this range itself? That is where interpolation comes into the picture. And again, as always, since we're discussing it in SciPy, there is a sub-package that will help you do this easily. So you can perform one-dimensional or any sort of univariate interpolation. Univariate basically talks about one variable, right? So one variable interpolation is possible, and even multivariate interpolation is possible, as in you can use 2 or more variables to perform interpolation. Now, when you say multivariate interpolation, it basically is also called a spatial interpolation. It is one of a kind where, you can run functions, and in these functions, you will have multiple unknowns, multiple known variables through which you can process all of them easily, right? So let's quickly head over to Python again, and let's take a look at how we can go about understanding interpolation in a very simple manner. Now, what we're doing here, as you can already see, is let me actually print it out so you have a better idea about what we're doing. We are creating a couple of plots here, and all of these are like functions, right? You can see that we've used the cosine function here. We've run this entire thing becomes a function when you take a look at it, right? A mathematical function to be very precise. And as you can see, we have certain data that we have just plotted it out, right? Now, if these two lines weren't there, the data would still have been there, but it would have not been plotted. The convenience of data visualization is all you have to do is like plot it out, and here's a scatter plot that will give you all the details that you're going to need. Now, one thing that you have to do is wherever we have a situation where we have to create a function based on certain fixed data points. Think about the example that I just told you, 0 to 10, right? Here's where interpolation comes into the picture. Now, if you want to understand what is the difference, what happens after interpolation, again, there's multiple types of interpolation, linear, cubic, and all of that. So all I'm going to do is I'm going to run this tiny piece of code here, and you can see this, right? Your actual data. Look at this. This is the data that we have in hand when we ran this cosine function, and all those blue dots that you see is exactly that graph. But over that graph, when you perform interpolation, we have linear interpolation on the solid yellow line, and of course on the dotted green line, we have cubic interpolation, right? Now, the way of us finding out how we can go about printing and knowing all these values. Now, you might be saying, okay, so why did we do this? Why do we have a graph there? Guess what? Between this blue point and this blue point, right? Two data entities. If you want something in the middle, if you want something in between these 2 points, guess what? You can have it now. But right now here, if you just look at the graph, you can still sort of get it. But unless you draw the shortest path, unless you start drawing straight lines from each of these entities, you will not get to know that, right? If I just gave you this and say, hey, now my mouse is pointed here, where is this? You can only guess, but you can't be specific. But if I say, hey, where is this point? Right now, where my mouse is, you can quickly map the x-axis, map the y-axis, give me a very accurate number of how you can do this. Again, all of this is done with the 2 lines of logic out here and a couple of lines, right? Again, 2, 3, 4 lines. So all in all, 10, 15 lines, you're done with understanding a simple interpolation. So we have created 2 functions here, function 1, function 2, and all the sample points and variables that are associated with it, you can see here, right? You can see X, Y, and the way of how you're supposed to go about interpolation, doing interpolation. There's multiple ways. Linear and cubic are the popular ones that you can go about seeing. So we took something that looks as plain, as boring, as uninformative as this, to understanding every single point that lies in between these 2 entities that we have in discussion, right? So at the moment, you understanding that you can go about doing this in a very easy way is the goal here. And I'm sure you can know the fact that if this simple small example can give you this much insight, think about actually using this in a scientific computing environment, right? There, you're going to have a lot more fun working with that. Right? Super. Now, as I told you, interpolation is basically a process of estimating unknowns that fall between 2 values. As we already saw, we have a library to go about doing it. We took a look at that practically as well. Right now, we discussed all of these multivariate interpolation, spatial interpolation, and all of that. So I'm going to run through the next type of sub-package that we have to discuss, which is Linalg. Linalg, as you already know, stands for linear algebra. And whenever you have a requirement that says, hey, I want fast linear algebra capabilities, guess the sub package that you're going to be using, right? Now, this sub package is actually built using something called Atlas. Atlas is absolutely fantastic. It stands for Automated Tuned Linear Algebra Software, and LAPACK. LAPACK basically stands for Linear Algebra Package, and BLAS, or BLAS as it's called, it stands for Basic Linear Algebra Subprograms. Now, these libraries, this is one library that is built using all 3 of these other optimized libraries out there. And if you can already think, just look at the naming. It seems like this is extremely complex, right? It is. And when you bring 3 extremely complex libraries and give the power to it to one single library, you must expect that, hey, this becomes way more complex than we started out initially. That's not the case. It actually becomes very, very simple of how you can work with all these algebraic routines. You can operate on multiple objects, convert it into 2-dimensional arrays. If you want an output to be a 2-dimensional array, guess what? That is also possible here as well, right? Now, if you are wondering at this moment of time saying, hey, so, this sub package that we have, it also provides us with functions to solve algebraic equations. So should you use if you use NumPy, here will be your confusion. Should you use NumPy.linear algebra or should you use SciPy.linear algebra? Well, SciPy.linear algebra contains everything that NumPy.linear algebra brings. And apart from that, what did I tell you previously? That SciPy is built on top of NumPy. So with all the functionality of NumPy and then some is what you will get when you use SciPy.Linalg, right? So if there is ever a confusion in your head at any point of time in your learning which says, I don't know which to use, now you know which to use, right? And it's not just that. There's another advantage here. The other advantage of using SciPy.Linalg over NumPy.Linalg is the fact that it will always be compiled ready with BLAS or LPACK support. While for NumPy, it still is supported, but it is optional. It doesn't come as a standard entity that you can go about using. So the speed at which your equations will get solved is way faster with SciPy.Linalg rather than NumPy.Linalg, right? I know it sounds a little bit complex, but trust me, this simple slide will give you all the information you need to know about quick comparison, what can do what better, which should be used when, what is the advantage of SciPy.Linalg over NumPy.Linalg, right? Again, as always, let me quickly show you one or two demos on this and, we can go about doing it. Now, I'm going to take you back to your college days. I'm going to take you back to your school days because look at this. This is a linear algebraic solution, right? Now, when you take a look at the various equations that we have here, all we're trying to do is we're trying to solve these three equations and we're trying to find the value of x, y, and z for whenever these equations become 0, and you can eventually find out, right? So all we have to do is we have to move a couple of things around. We have to multiply certain equations with certain entities, and then you can get to solve. You start eliminating your variables. You solve for one. Once you start finding x, you can find out y. Once you start finding out y, you have the value of x and y. Use it to find z. That is how we solve it. Now, I definitely can do this manually because I remember how we can go about doing it. But to get our linear algebra system to work with, we're going to be using all the inputs as arrays. Now, as you can see, right, it's 1x, 2y, minus 3z. Look at this, 1x, 2y minus 3z. The second equation is 2x minus 5y plus 4z. And then you have 5x, 4y minus z. Minus z is nothing but minus 1, right? So this is the input array that we have, and here is the solution array that we require. And guess what? You have you have the input, you have the solution. All you have to do is solve it, right? Get from that to this. Look at the line which talks about the logic of how you can go about doing it. One line of code, and as soon as I hit play, it's very easy, right? Look at this. One thing you have to understand is x is 2, y is minus 1, z is 1, right? It's 2 minus 1, 1. If you substitute 2 minus 1 and 1, your answer should be 0 in all three of these equations. This is what we're being told here. This is the value of x, y, z. And once you attach the value of x, y, z, or everything must be 0. If you get these values and these are not zeros, it means that your equation is not completely balanced out there and there's something that went wrong, right? Again, look at how, I know you would have thought this would have been very complex as we started out, but this was the equation. All we had to do is we had to move the equation, and we already know the solutions from the right side, minus 3, 13, and 5. All we had to do is create two arrays, run one command, print the result, done. Very simple, right? So this, again, at the end of the day, is very, very simple of how you can go about working with linear algebra. Let me give you one more example. If you guys have worked on matrices, matrix as it's called, there are a lot of types of matrix, diagonal matrix, square matrix, finding the determinant of a matrix. It's a very important concept in applied mathematics, right? So all we're trying to do here again is we're trying to create this matrix that we're talking about. To find the determinant of that matrix is again one simple function, dot det of a, where a is the values that you're going to be providing. Input, perform the operation, output. 3 lines of code and you're done finding the determinant of a square matrix. Now, to do this manually will take a lot of time because you have to go about processing it and work with it. I'm very sure if you have taken up probably engineering for your bachelor's, you might have worked on these in your first 1 or 2 years of engineering, right? Understanding what a matrix is, operations, determinant, all of that. Now you can take a look at, this is the matrix that we have in hand, the matrix, the square matrix that we are discussing. It's a 3x3 matrix, and this is the determinant that goes with that matrix, right? It's very simple. At the end of the day, it just takes a very complex solutions, simplifies it by a lot, as I told you at the start of the video, and I'm sure you are convinced of that by now, right? So let's quickly take a look at another last sub package that we have in hand, which is Ndimage. Ndimage stands for n-dimensional images. It's an image processing library which you can use to perform multiple processing tasks, and you can perform various analysis out there as well, right? So the first question you must be asking right now is, hey, we have OpenCV to do this task very easily. Why do we require this? There might be cases where, there are cases where SciPy might trump OpenCV out there. OpenCV is meant for computer vision, meant for images, meant for videos, but SciPy is not lagging in any regard, right? Take a look at the basic manipulations that you can go about doing. You can crop an image, you can flip an image, you can rotate an image. You can do all of these simple tasks by making use of SciPy itself. And if you ever have to perform image segmentations, right? If you have to understand what's going on in your image, what the pixels in a flower looks like, what the pixels in a car looks like in an image, you can go about doing all of that. You can perform classification tasks using your images. If you want to build a dog and a cat classifier, as in you'll provide input images of dogs, input images of cats. You will get your machine learning algorithm to understand what a cat looks like, understand what a dog looks like. So when you surprise it with another image, a random image of either a cat or a dog, it will have the capability to tell you if it's a cat or a dog. How cool is that, right? It's a simple binary classifier, which again, I love working with. And of course, you can do all of that. You can do feature extraction as well. If there is a case where you know this is what the solution is, this is my application, and if you're wondering what variables in your data will let you go towards the solution, the process of feature selections, feature extraction is very, very important, right? There is a very wide term which governs all of these feature concepts. It's called feature engineering, which you might have heard about if you've studied a bit of machine learning, right? Fantastic. Let's quickly go about taking a look at this demonstration. This one's going to be nice. We have a couple of images that you guys can take a look at. Now, all I'm trying to do is we're trying to print scipy.miss.face is going to print an image of a raccoon, and this is what a raccoon looks like, right? Looks pretty cute in my opinion. And all I tried to do was we took the image of a raccoon, and all we did is we printed the image using matplotlib. You can see that plot.imshow stands for image show here, and this is the overall plot that we got. Fantastic. Now we have an image to work with. What are the one or two tasks that I can show you about how you can do? The first thing that we can go about doing is cropping the image. Cropping, this is the heart of the logic, right? One line of code, you can crop the image. Look at this. Now you have an entire raccoon out here with like a lot of grass on the top right, a lot of, I think palm trees on the bottom left or whatever it is. And now you can crop it. Now, if you're wondering about how you know where to crop and what to do what, you have something here called face.shape, wherein we have X channels, Y channels and all of that. And through which when you run integer of, LXPy4. So we're basically trying to say, pick up everything around the face and just crop it to us and just go about printing it. Right now, what I want you guys to do is, as soon as you see this code and you're trying to type it out, just change these values to see what output you get, right? Of course, changing these will change what and where the cropping happens. And I want you guys to figure this out. Now, don't Google this. This is very simple. You have to change one or two numbers. I've already told you what to do. Just give it a shot, right? So this is us taking an input image to us cropping an image. The next thing you can do is you can take an image and rotate it at any angle that you want. Now here all I've told is ndimage.rotate face by 180 degrees. Now all I can do is as soon as I hit play, you will see that the entire image will be flipped by 180 degrees. Now this is not the cropped image, right? Because we're still using the original image that we have in discussion. This is the input image. This is the output image. You can see that it just went all the way over to that particular angle, right? So as you can see, working with even basic image operations, working with linear equations, working with interpolation, working with constants and clusters are very, very easy with respect to SciPy. Right, guys? So with this, we have come to the end of this course on SciPy and Python. I hope you guys are clear with everything that we have covered today. We started this course out by taking a look at, first of all, understanding what is SciPy, why do we require SciPy, where is it used, how good is it, how popular is it, right? Now, once we understood everything you need to know about the basics of SciPy, we dived right into installing SciPy. Now, I'm sure you guys being Windows users, Linux users, Mac users, you found your section in the course wherein you could install it with ease. And after installing it, we understood the various sub packages, right? We took a look at 18 sub packages, and there's more to understand what the power of SciPy is. After that, we took a couple of sample sub subpackages and worked with it. We worked with constants, we worked with interpolation, we worked with image handling, we worked with linear algebra. It is such a fun thing to take a look at, knowing that, there are some things which are very complex, and you might think, hey, this is a very complex mathematical thing to solve manually. How can you solve it on a computer? It has to be more complex, right? I'm sure enough I've changed your mind to tell you that you have actually simplified a very complex process. That was my sentence at the start of the course, and here is me telling you that, hey, I hope that I've convinced you on all of these, right? So we took a look at a various amount of sub packages out there, knowing all the basic operations, all of these foundations that you guys can go about using as a foundation to understanding how you can build your own applications and devise your own solutions in any domain that asks, right from signal processing all the way to machine learning, right? So guys, fantastic. Thank you so much for watching. My name is Anirudh. I'll see you on the next one. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleagues, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.